Okay, the theme of deep time inspired the geochemists to agree to give their lectures in a sort of a broad time succession. So you've heard Rick talk about stardust, about the prehistory of the molecular cloud that was going to collapse to eventually make our solar system. The generation of refractory minerals as that collapsed nebula cools down, and the production of the first solids at 4.568 billion years, give or take, which is a good number to store in core as a sort of starting point reference for a discussion of the early solar system. Rick talked about volatile depletion in planetesimals and other bodies, evidence from manganese chromium, you folks remember, that suggested a duration of about 10 million years. Then you heard Bill talk about the moving target that is our understanding of the composition of the bulk Earth. So I'm going to pick the story up about 10 million years into the evolution of the solar system. And for discussion's sake, I'm going to assume that something like the majority of the Earth has accreted. And then continue and talk about the first 558 million years of Earth history. Why 558? Simply, it's convenient for us to define the period, at least informally, prior to 4 billion years as the Hadean. You see the Hadean here on a time scale with major milestones in the evolution of the Earth and life, including, as you can see, some really good adaptations occurred along the way. The situation at about 10 million years in is interesting because we have a resounding lack of geochemical evidence that there was a magma ocean on this planet. Yet, as you heard Dave Stevenson say the other day, the energy inputs available to the Earth at that time were so great as to essentially compel us to assume that there was one or a succession of magma oceans occurring in this interval. Again, as you heard a little bit, and we'll hear more about, depending on atmospheric conditions, the calculations suggest that magma oceans could largely crystallize in timescales ranging from a fraction of a million years to perhaps 10 million years. Given that there's,
You didn't talk about the origin of sex. How do you know that? She was there.
It's, yeah. It's not really what my focus would be, but.
It's the only time I've ever seen a geologist talk about that.
No, it was a good idea. Obviously, I wouldn't be having this conversation with you. We would have, in fact, instead of having something like after 20 generations, you can generate 10 to the 40th genotypes with having sex, whereas if it's simply mutations, you obviously get roughly 10 to the 39th fewer generations. So it was an important takeoff point in evolution of life. Where was I?
Interesting digression.
The isotopic variations from mantle-derived rocks suggest, or at least are consistent with, this period of magma oceans potentially being over. In fact, all those violent things you've heard about, moon formation, formation of the core, formation of magma oceans, differentiation of the silicate Earth, potentially over by about 4.53. I mean, you can make a consistent argument that is that doesn't violate many geochemical constraints. But what I'm going to say is, let's say that it's 4.53. So that brings us about 40 million years into solar system evolution. But I'm going to put an asterisk there. So 40 star is essentially a metaphor for whatever that time truly is. But in fact, most of the isotopic record indicates that, or is consistent with this history. Recent observation, for example, of tungsten 182 variations, could be interpreted as indicating that magma ocean formation, the lunar impact event, in fact, was over by this time, or in fact, it may be reflecting incomplete mixing, in fact, due to from a magma ocean that's considerably younger than that, or in fact, as Rick pointed out the other day, late inputs in this case of radiogenic tungsten. I'm not going to talk a lot about this, but I wanted to really underscore the change that's happened over the past 10 years with the advent of the latest generation of high sensitivity accuracy mass spectrometers. These variations that we are now seeing, and to some degree that rapidly changing list of papers that Bill showed us yesterday reflect this newfound power of these isotopic tools. I'll give you an example. These variations that Rich Walker and his group have seen are on the order of 15 parts per million. And what I like to say, especially to a Southern California crowd, is imagine the Rose Bowl on a Saturday, which UCLA is losing to some other Pac-12 team, but the place is packed out. There's 100,000 people. If one of those members of the audience gets up and goes to the toilet facilities, the mass of the Rose Bowl has changed more than the precision of our ability to see the difference in two tungsten isotopes. I mean, that's 10 ppm. And in fact, in some of these systems, it's as good as a factor of 2 or 3 times that level of isotope ratio precision. So the reason the story is so much richer and more interesting today than 10 years ago is in part the fact that we've sharpened the tool one extra order of magnitude, and we're seeing things that were opaque before. Okay, so what was the Earth like after the last magma ocean at 40 million years after first solids? Despite the fact that there's essentially, a paucity of lithic record from prior to 4 billion years, we in fact had made up a story that the planet looked more like this than anything else. That it in fact was ocean-free, it was potentially molten, continent-free, certainly lifeless. I offer you this. You could read this faster than I can recite. But this is a book, a pretty good book generally, published I think 10 years ago, or maybe even less than 10 years ago, by Ward and Brownlee. It underscores the fact that about 10 years ago, there was general agreement that nothing much interesting had happened prior to 4 billion years on the planet. It was just this page. You had to wait through this phase when everything was, molten and things were winging in from outer space and disrupting. Particularly, what I want to focus on is that this general consensus, although there were a few eccentric outliers, but this general consensus that there were no continents prior to 4 billion years, part of it kind of is intuitive. We haven't tripped across evidence of a continent older than 4 billion years, so it never existed. Okay, well, maybe the planet recycled back then like we in fact can observe it recycling today. And also there were in fact many arguments, largely fallacious, that the Earth couldn't have had a flotation crust immediately upon following accretion like the Moon manifestly did, mostly because of the behavior of the mineral plagioclase. Okay, they, if at least the part of the magma ocean that we're going to care about at the surface, if the magma ocean is crystallizing towards the surface, you're certainly going to make a quenched crust at the top, a komatiitic or a basaltic crust, but that's not stable. It's going to founder on some time scale that's difficult to calculate. Whereas the Moon produced seemingly a plagioclase flotation crust, seen in the lunar highlands. It was thought that we couldn't, and that's because if we are hydrous, if we've got an ocean or two of water in the Earth, and it's at least partly in the magma ocean, that plagioclase crystals, especially the calcic-rich ones that are going to crystallize in this conditions, that they in fact are denser than the liquid. That's oddly enough just not true for the sort of iron contents that you'd expect to be in equilibrium with. The other thought was that in fact in hydrous melts, the plagioclase crystallizes very slowly, so it would take too long for plagioclase to grow to a size where its Stokes ascent velocity was greater than the violence of the turbulent fluid behavior around it. And so in general, it was thought that this idea of us being continent-free reflected the fact that we couldn't behave like the moon. Tony Morse, some time ago, back in the 80s, proposed this model here, where as the magma ocean, in fact, base is getting close to the Earth's surface, say, with 200 or 300 kilometers, that olivine is the only phase on the liquidus, and you produce a remarkably felsic liquid. That is a liquid that, in fact, is going to want to eventually crystallize plagioclase when you get into the stability field, but leave that out of it. Simply, you're going to make a buoyant liquid that will accumulate and then ascend, and his thought was that this felsic liquid will be network rich. It means this is going to be potentially a polymerized viscous liquid, have the ability to dissolve a lot of water by breaking up the network, and that once that buoyant if felsic liquid reaches close to the Earth's surface and ambient conditions, that it would in fact rapidly crystallize a protocrust. And in fact, experimental evidence is not inconsistent with this. If you look, here's work from Ashihara and Otani, and you can see at depths between, say, 250 and 300 kilometers, at least with some extrapolation, that olivine, the square open symbol here, is the only relevant phase, so Tony's model is valid. And in fact, you're outside the stability of garnet here, the red line, which is a killer because the presence of garnet will suck up the major elements that the continent wants to have. So garnet is a continent killer. So there are conditions towards the end of a magma ocean when in fact a flotation crust is plausible. I'm not saying we have any evidence for it, but you'll see shortly why this is not an unattractive idea, because we are going to need a raft to hold some almost as ancient as 4.5 billion year material to bring to the present day. And here's one way of.
I'm not going to say that that's impossible, but it requires a certain number of assumptions about how the magma ocean dynamics behave.
Oh, absolutely. No, absolutely. But what I guess my point is that for 40 years, the folks in the lunar community have been saying that this is impossible. So I'm just opening up the subject for discussion.
Mark, another important distinction I would note is that plagioclase is stable almost throughout the whole universe.
Remember, yeah, good point. Okay, but Morse isn't asking plagioclase to be stable. He's asking a felsic liquid to be stable, and then, in fact, getting close to your surface where plag is stable, and then you would rapidly crystallize this. Yeah, so simply a starting point for us. Is it feasible for us to have a felsic initial crust? Under certain circumstances, it's not ruled out, which has been sort of the paradigm for 40 years.
What you're hoping for is to get something floating on top of the magma ocean so that there's something stable, while in the interior the Earth is largely molten.
No. I'm saying the last couple of hundred kilometers.
The ocean, is done crystallizing, and the last scum is kind of differentiated or has created some volcanic activity afterwards. If you put up a timescale there of 10 to the 4th to 10 to the 7th years for crystallization of the magma ocean. So, it's quite plausible that the magma ocean crystallizes fairly quickly.
Yeah, sure.
The end stage of it really doesn't care whether or not the differentiation process did what you just suggested. You still have to.
So, crystallize until it's 50 kilometers of mold, and then simply fractionally crystallize. That's you're not going to get the same volume of protocontinent by doing that as if you would just start at 300 kilometers.
So we tend to think that the magma ocean is this
Right. One of the assumptions in this calculation, in fact, is that the magma ocean, in fact, has crystallized without strongly fractionating the liquid, because that's actually assuming a pyrolytic source. It may well be that, in fact, that's a very conservative assumption, that the residual liquid at this point is much more felsic than Ashaheronotani used. Okay, so what have we got? This has all been speculation up to now. What do we have in hand? We can make a reasonable assumption that physical laws are constant through time, so we know what radioactivity we can anticipate, or at least the relative amount. And Hadean maybe 3 or 3.5 times as much as we have today. We assume it was a very violent place. But we're going to have to be very sneaky about how we approach the lithic record, because we don't have much. And what we have in part is the zircons. Okay, I'll introduce you to that in a sec, that are nearly 4.4 billion years. A putative 4.4 rock suite from northern Quebec. And these isotopic variations, most of which, in fact, have been revealed in the past 10 years as a result of this enhanced precision and accuracy from mass spectrometers. What do we see in these various systems? We see fractionations in extinct isotope systems. Rick talked about that, largely in the context of solar system formation, but there's overwhelming evidence in the zircons, and actually in this rock suite here, the evidence of the presence of water at or near the Earth's surface, and I would argue magmatism in low heat flow environments. How do I interpret this? You can see that the Earth differentiated much earlier than previously thought. There was a hydrosphere almost immediately, some continental crust. It's not something I can quantify, but there has to have been a raft of some kind, and possibly even plate boundary interactions.
How do we see magnetism in low heat flow environments?
Why don't I give my talk, and it will be revealed in the fullness of time. Okay, yeah, I'm going to actually dwell on that nauseatingly. So let's talk about this mineral first, this zircon. This is what we've got in hand. Zircons between, say, 4 and almost 4.4 billion years come from Western Australia. I'll show you the site in a sec. But this doesn't give us much, okay? 92 elements in the periodic table. We've got 3 of them here. So what can this simple phase tell us? Well, like I think Bill emphasized yesterday, every mineral has got every element in it, okay, at some level. And zircon's no exception. Zircon likes, for example, rare earths. It really actually likes heavy rare earths a lot. Okay, you can see the color scheme. It likes hafnium a lot. And hafnium, in fact, we've told you, is part of the lutetium hafnium beta decay scheme here. It likes uranium, thorium, and even, oddly, plutonium. I've got in here because, in fact, we're going to use all 3 of these systems. There's lots of oxygen in zircon, right? It's 2/3 oxygen, so maybe we can do high-resolution oxygen isotopes. It doesn't like titanium much, but in fact, it's going to turn out that this has got a real rich story to tell us, potentially, about water in the early Earth. Okay. Now, these 3 systems here, they're all radioactive. Uranium and thorium are decaying to lead isotopes. Plutonium, in fact, is decaying by several mechanisms, including spontaneous fission, to create fission xenon isotopes. And we'll talk a little bit about that and more in the tutorial next week. But let's have a look at these guys here. Why don't I give my talk, and all will be revealed in the course of... Okay, so I'm setting this up. No, I'm not going to breeze by anything. We're going to come back and... Oh, yes? Oh, well, good question. Okay, so how are these things substituting? Titanium actually, is an irritant in zircon. It's present at a level that's 3 or 4 orders of magnitude less than what the zircon grows from, typically. And oddly enough, it likes to substitute in for silicon. Okay, hafnium, you can see, is right under here, right under zirconium. In fact, Hafnium is obviously going to substitute for zirconium, and in fact, happily so, although that's the ostensible formula, 1 or 2% of a zircon is typically hafnium, and so on. And phosphorus is there because, in fact, some +3 cations have snuck in and used the phosphorus and other elements with anomalous charge or different charge structure to jointly substitute, and which allows, for example, this range of rare earths to be incorporated in zircon. So it's if it were perfect, we'd be out of luck. But as I say, essentially every element under the sun and is available in a zircon for us to study, albeit at potentially very low concentrations, others very high. Okay, let's look at the systematics. Rick raised this. I thought I'd put it in just to remind you that the concept here is you have a radioactive system. Uranium and thorium are both unstable. They're trying to decay down to iron if they could. Instead, in fact, they're going to decay to different isotopes of lead for the moment. If you start out here with 100 radioactive atoms, in fact, the rate of decay, okay, the rate at which the parent is decaying to the daughter product is uniform with time. So the fraction of atoms that are decaying per unit time is constant, such that in fact after you've lost half of the parent atoms and in fact generated an equivalent amount of daughter atoms, the daughter to parent ratio is 1. Okay, so if we know the decay constant, the fraction of atoms decaying with time, we in fact can characterize the half-life, the time it takes for half of the parent to decay to the daughter, and then just translate this to a more interesting plot. Okay, you can see that after we have 50 parents left, we've generated 50 daughters, so the daughter to parent is 1. Now we have 25 after 2 half-lives, 25 parents left, 75 daughters generated. So the daughter-to-parent ratio is 3, and it goes on like this. Then after 3 half-lives, it's 7. The daughter-to-parent is 7, 15, 31, 63, and so on. So this is an interesting plot. What it's saying is that if we can measure in a geological sample the daughter-to-parent ratio, the number of daughter atoms per parent, then it's a unique function of age. Let's say we have a half-life of 1 billion years, then a 4.5 billion year old rock sample or mineral should have a daughter-to-parent ratio, or would have a daughter-to-parent ratio of 23, right here. Okay. If the half-life were 10 times that, the age would be correspondingly older. Yeah, question. In depending on the system, we're going to be talking about alpha and beta decay. But for example, in electron capture, if at core mantle boundary sorts of pressures, there actually is an influence because the innermost electron is closer to the nucleus. It actually enhances the rate of electron capture. Or in fact, if you're in a plasma, and there are no electrons, obviously the electron capture is interfered, but not for these systems we're going to talk about today. Say again? No, there's no ostensible effective pressure or temperature, right? Okay, so now we have 3 different isotopic systems in uranium thorium. There's 2 long-lived isotopes of uranium, uranium-238. That's 99% plus of modern uranium. 235. This is, if you were an evil dictator, this is the one that you want to enrich to build a bomb out of. And you'll see that 238 decays to lead-206, 235 to lead-207, and it throws out some alpha particles and beta, and there's decay energy. The half-lives are fortunately rather different. The half-life of uranium-238 is about the age of the Earth, about 4.4 billion years. The half-life of uranium-235 is 700 million, okay? And this actually works well for us. I'm not really going to dwell on this for the moment, but to point out that we get an age equation for the uranium-238 decay system, lead-206-238, and we get an age equation for 207-235. If we were to plot these parametric in time, you get something called a Concordia plot. Okay, so we're plotting the uranium-238-206 system here, and here's the 207-35. So these are things that we can measure. Let's say that we have a sample that's 4.4 billion years old. What's the 206-238 ratio? Well, I've told you the half-life is about the age of the Earth, so it makes sense then that a 4.4 billion-year-old sample should have a 206-238 ratio, parent-daughter, of about 1, because it's been through one half-life. On the other hand, in the 235-207 system, the daughter-to-parent ratio is much higher because we've gone through, 6.5 half-lives of 235. Okay. Now, the cooler thing about this, if the two half-lives, if the decay constant here of 238 and 235 were the same, this would be a straight line, okay? That wouldn't be very interesting, because if our sample here, 4.4 billion years, and that's old, and there's a lot of potential for bad things to happen. Let's say that sample there loses 99.9% of its lead yesterday, so it comes all the way down here, but not quite to the origin. We've lost, 99.9% of the daughter product of the lead. We can still calculate an age from the ratio of lead isotopes, from lead-206 to 207. And even though this thing has lost the vast majority of its daughter product, the lead-207 to 206 age is still 4.4 billion. Okay? And it's because of this curvature that allows us to do this. Okay, now, we need a big ion microprobe for this purpose, because the zircons we're going to get from Western Australia, I'm going to tell you more about, they're tiny. They're typically about a nanogram each, a spatial scale of maybe 100 microns in the big dimension. And if we're going to do experiments, if we're going to understand the Hadean, we're going to want to preserve as much of that zircon to interrogate it by a variety of radioactive and stable isotopic systems as possible. So what we do is we, in fact, utilize these big geometry ion microprobe. Okay? And in fact, here's an example. Here's a 3.3 billion year old zircon that has a 2.6 billion year old rim on it. And we just made these little spots. Each of these spots is about 1 nanogram. So it's about 1,000th of the mass of one of these zircons. And the way it works is we get a focused ion beam, typically about 10,000 volts, and we take that focused ion beam of about, anywhere from about 1 to 20 microns in diameter, and we hit our geological specimen, or in this case zircon. Okay, so we analyze this region here, and it sputters. That's the verb, off secondary ions from the sample that we then accelerate into a big mass spectrometer, shown here, and I'll show you more in the next slide. And the mass spectrometer has to be really big because we, in fact, have done something very bad by the sputtering process. We, in fact, have manufactured a zoo of artifactual molecules. Okay? For example, this is a zircon is simple, ZrSiO4, right? But here's what the mass spectrum looks like up where we're interested. Here are the lead isotopes between 206 and 208. But there's hafnium I mentioned in there. There's all kinds of things. And we, in fact, have created a real mess for ourselves. So we need to get a physically very big mass spectrometer in order to mass resolve. For example, the mass spectrometers Rick was talking about this week, in which he's doing these exquisitely high precision measurements, have a mass resolving power of about 500, okay, or 800, but something like this. So here's mass 206, 207. If my mass spectrometer had that mass resolution, the ability, and essentially the mass resolving power of 500 means I can detect a mass of 501 from a mass of 500. Okay. What we need is something up around 5,500 or 6,000, because at that level, what would have in fact been captured under this peak at the low mass resolving power turns out to in fact be 3 peaks, okay, different molecules, and that's the guy that we're interested in. That's the lead-206, that's the lead-207, and that's the lead-208 there. So these things are gigantic as mass spectrometers go. They typically double focusing. We're going to want to take those secondary, here's the primary source, we focus that ion beam down into the sample, sputter off secondary ions, and then put it into essentially a mass filter and an energy filter. This is a funny mass spectrometer, and this is the mass filter here, and we detect the ions down here. So this is where we're going to make the isotope ratio measurements. Mass spectrometers love to very, very, very precisely give you the wrong answer, okay? And so you have to be, one of your jobs as an isotope geochemist is you have to find a way to translate that very precise wrong number to something that's accurate and meaningful. Ion probes have another cross to bear, and that is they love to tell you about isotope ratios, like lead-206 to 7, piece of cake. But uranium lead, okay, that's the full decay, they don't much like that. They really want to try and give you the wrong answer. So you have to fight against what are called matrix effects. Every different mineral that you look at has the secondary ions that we're sputtering, in fact, have different ionization efficiencies. So this is something we struggle with. So we're stuck with a precision of isotope ratio measurements from the uranium lead system of about 1%, or maybe if we're 1.5%, something like that. Where Rick is making 10 ppm or 5 ppm measurements. So these are very different instruments. On the other hand, we can make lead age measurements to potentially 0.1%, and in fact relatively routinely. Okay, so now we've got a big device that we're going to be able to just take a nanogram of our zircons and analyze. So we're going to be able to characterize.
It seems like there are up to a few hundred to maybe even 1 billion years of age difference across some of these zircons, and the spots are not zero size. How much
Yeah, you can see in that image I showed you that the zircons are. The question is, you've got 1 billion years age difference between the core and the rim. What happens if you overlap? Well, I say zircons, as you saw in Jeroen's talk the other day, they help us out by essentially having growth rings, like growth rings in a tree, so you can sort of qualitatively make judgments about this. You don't have to use an ion probe in spot mode. Imagine this table is my zircon, okay, and what I do is, I'm going to polish the zircon, and I'm going to analyze, I'm going to grind it, and I'm going to analyze the age of the spot. That you could do, or if you wanted, if your zircon has a rim, tip the zircon up so this narrow rim is exposed, and then drill perpendicular to the surface. In which case you go from a spatial resolution of 20 microns to a spatial resolution of 100 nanometers by depth profiling. So it's nice that zircons aren't spherical, that they have these tabular, or prismatic boundaries, because it's possible to increase the spatial resolution in certain cases by a factor of 1,000. And it may look like the zircons have, a spectrum of ages, but when you do careful studies, what you see is zircons. 50% of all zircons documented in literature don't have a simple single-age core. About another 40% have one rim. About another 5% have 2 domains, and I think there's only 2 documented cases in the literature of there being 3 or more rims. Although having a core rim relation is common. You know, virtually 50% of all analyzed zircons have such a thing. Documenting multiple episodes is extremely rare. So there's something about zircons that wants to make them shed earlier growth rims, because clearly some zircons have N plus 10 orogenic cycles, or have seen that, but yet they don't come with 10 different concentric rims. Okay, really better get moving here. So what we've in fact done is we've gone to this part of the Jack Hills in Western Australia and done this the hard way. We've in fact separated out from these rocks here 170,000 zircons, about 2.5% of which give ages older than 4 billion years. And that's given us 5,000 zircons to play with from the Hadean, between 4 and almost 4.4 billion years old. And we've done various analysis, and I'm just going to give you a brief resume here. Some of the zircons have high del-O18, have high heavy oxygen, which I'm going to describe this to you, but in fact suggests to us that the protolith, the rock material from which the zircons formed, had in fact once been clay. And clays have one thing in common: they need structural water, and they form at or near the Earth's surface. So this is some inference that these things were formed near a planetary surface that had water. This is remarkable. Thermometry method developed in the course of the Hadean project indicates that these Hadean zircons formed at a 680 degrees. Why is that interesting? It's because this is so close to water-saturated minimum melting in the granite system as to be remarkable. Some of the inclusions show compositions that are consistent with what you might see in the Andes today in a convergent margin, and other inclusion assemblages are more typical of what you'd see in continental collision, for example, in the Luca granites that are exposed in the high Himalaya as a result of the Indo-Asian collision. And in fact suggest that there was a sedimentary cycling system going on in the Hadean to produce this dichotomy. And lastly, and this is not something I want to emphasize, but we're going to talk about, I think you asked, or somebody asked, how do we know there was plutonium? Because plutonium produces a characteristic xenon fission spectrum. And these zircons were around at the time when plutonium-244 was active in the solar system. Barbara? It's you back a pickup truck up to an outcrop, and we keep going back to the same outcrop. We've sampled more broadly, but the discovery outcrop is right about here. So we know that there's 2.5% or so Hadean zircons. So we simply back it up, whack the rock off, take it, crush it up, fine, turn it into sand. The rock I haven't shown you. It's an uninteresting looking dirty quartzite, and so that the particle size is order tens of microns or 100 microns. We put it through a heavy liquid, so we take nasty materials like methylene iodide, things that want to rot your liver, cause narcosis in dogs at the 50 ppm level. So you want to do this in a fume hood, and this has methylene iodide's density of 3.1 grams per cubic centimeter. Zircon is 3.3. Or can vary depending on its radiation damage. So the heavy minerals sink. We can recover that, concentrate that, and then a nice lady picked out 170,000, well, about 160,000 zircons, and put them into epoxy mounts of 20 rows and 20 columns, 400 zircons to a mount. And when we started this project, it took 15 minutes to date a zircon. And this just wasn't going to work. And by the time we finished the project, we had gotten it from 15 minutes down to 6 seconds. So we can characterize the age of one of these grains with 6-second isotope analysis in the big ion probe. Okay, well, let's start with lutetium hafnium. It's already been mentioned, lutetium-176 beta decays to hafnium-176 with a half-life of 37 billion years. But here's the thing. I'm not going to use this as a geochronometer. What would the daughter-parent ratio be here in this system after 37 billion years? It would be one half-life would be 1. Yes, okay. But 37 billion years is 4 times the age of the universe, right? So this is a very, very slow decay system. Anyway, so have a look here. Rick was talking about this concept of sort of epsilon. This is a difference in parts of 10 to the 4, in parts of 10,000. So in fact, something that plots along 0 has what we think is the bulk hafnium 177 ratio of the solar system and Earth. Okay, so if you plot along here, you simply, between say 4.4 and 3.4 billion years, you're evolving as though you had the average lutetium hafnium ratio of the solar system and of the Earth, although those two may well not be the same thing. This line here, Beth Ann, why do we call this PHB? Okay, I call this the forbidden zone because this represents isotope compositions of hafnium that are lower, okay, or more primitive than the initial hafnium isotope composition of the solar system. So you can't go here. But the thing to point out is these, and what we're looking at, in fact, is essentially all Jack Hill's zircons, is that you get a real broad distribution with most of the results plotting here, sort of pointing back to very old, very ancient extraction ages, but some of them, in fact, are plotting right down at the boundary. This, in fact, represents the initial isotope composition of the solar system. So to get here at 4.32 billion years, you essentially have to have been taken out of the global silicate system and removed into a reservoir that has, for all intents and purposes, a lutetium hafnium ratio of 0. And the best candidate for that right now is the continental crust. Okay? Now we can take these data and say, what's the range of lutetium hafnium ratios in this kind of magmatic rock or that kind of magmatic rock, and we can make model ages out of this to see when those zircons could reasonably have been extracted from the bulk Earth silicate system. And the results are shown for this simple model up here, Monte Carlo model, where we've taken the data. And you can see that we simply don't allow ages older than 4.56 billion years. But the zircon, this cloud of zircon data, in fact, is indicating that for as far as these zircons are concerned, they started popping out of the bulk reservoir, the bulk Earth reservoir, by as early as 4.5 billion years. And I thought I should, in fact, show you that lunar zircons actually look a lot like this. Here's some data from our lab showing zircons from Apollo 14 samples, and they array in this way, suggesting or pointing towards an extraction age of about 4.5 billion years. But in fact, even better than that, we've taken the lutetium hafnium ratio of creep. I don't think we mentioned creep thus far. This okay. A ratio independently determined from whole rock lunar chemistry, and we drive that through there, and we get an extraction age very close to 4.505 billion years. So it's a model age based on this ratio. It's inconsistent with the alignment, but it suggests that whatever happened to the moon, you better have gotten it out of the Earth by 4.5 billion years. Okay, now really changing gears here. Titanium-in-Zircon thermometry. This, in fact, is a method that was developed in response to the early Earth project here. The observation is that if you look at the log titanium concentration in a zircon that's in equilibrium in a melt with rutile, with titanium dioxide, there is a simple Arrhenius relationship between the temperature and the titanium concentration. So, for example, what's at 10 parts per million in a rutile saturated system, that would correspond to a formation temperature of about 780 degrees. And the cool thing is, titanium just doesn't want to diffuse in zircon, okay? You can, for any reasonable crustal thermal history, titanium thermometry is in fact not going to be reset. It's giving you its best estimate. Now, what if in fact the rutile activity isn't 1? If it isn't what if it's in equilibrium with ilmenite or something, say an activity of 0.5, then around 600, 700 degrees, we're going to be potentially underestimating temperature by 40 or 50 degrees. Okay, well, what do the Hadean zircons look like? They give this bullet-like, this is more than 200 data. With a peak here at 680 degrees. This is remarkable because if you think about melting, and these are, as you'll see, essentially largely granitic zircons. In order to melt a rock at sort of crustal pressures, 680 degrees, you essentially have to be right on the wet melting curve. You need here at say 3 or 4 kilobars, you need 10% or 12% water in the melt. You have to have excess water. You have to have vapor present to produce this. So this immediately led us to infer that something quite interesting is there has to be a lot of water, at least relatively near the surface in the Hadean at 4.1 to 3 billion years, because we're seeing minimum melting. Now, zircon isn't entirely restricted to it's very characteristic of a continental rock. The likelihood of you going outside and picking up a rock and there not being zircon in it is highly improbable. But as I've shown you, there's zircons on the moon. There's zircons that can come out of mantle rocks, mafic rocks. What do they look like? The temperature spectra are considerably different. Here's the Hadean bullet here. Here's a broad survey of mafic rocks. Here's clearly you see the lunar rocks are off at the very high temperatures. The geochemistry is very different too. Here you can see on this trace element discrimination diagram that the Hadean zircons plot firmly in the continental field. These are not zircons that came from outer space. They're not from the moon. They're not from mafic rocks or morbs or kimberlites. These are continental zircons. Now, it's true that we don't know. These zircons got separated from their source, more than 3 billion years ago when the quartzite formed. So we don't know necessarily that these things were all in equilibrium with rutile, but the ones in which there's rutile inclusions are plot with a temperature of about 680 degrees. So those ones that, in fact, we can demonstrate are in equilibrium with rutile yield the same temperature distribution as the whole plot. But something that's interesting is these are sedimentary, these are detrital zircons, and somebody asked about this the other day, are there potential sampling biases and preservation? They are, but in fact they're going to work in the opposite direction. They're going to tend to make a temperature distribution of a detrital population look hotter rather than colder than they are. Why is that? Because, in fact, with the advent of the thermometry, we now know what we long suspected, and that is that high-temperature zircons have low uranium, and low-temperature zircons can have very high uranium of 1,000 or even tens of thousands of ppm. These zircons out here, they ain't going to last. There's no Hadean zircon that has a uranium concentration higher than 500 ppm. What happened? These are a real part of the population. What happened to them? They killed themselves, right? They had such high uranium, the radiation damage turned them into jelly, and they didn't survive the sedimentary transport process. So if you look at a detrital population, in fact, it's going to tend to overestimate the temperature of the source. Here's something when we finally developed titanium ion imaging, we're able to actually take an isotopic image of in this case, titanium. What we found is many of our original measurements, so here's truly 5-6 ppm. This is about a 780 degree zircon. But some of our measurements overlapped. You can see there's titanium that's come in on cracks. And we, in fact, had to correct our initial population or distribution to lower values because of this contamination. John Eiler and Amy Hoffman at Caltech have recognized that there's disequilibrium effects. That here's a Jack Hill zircon. You can see again typical temperatures, 660, 670 degrees. But there are excursions, okay, corresponding to many ppm uranium that they interpreted to be disequilibrium accommodation. That is, you're growing a zircon in the melt. Okay, and the zircon's excluding everything else except zirconium, hafniums, right, silicon. But the concentration builds up. You make this, snow plow of stuff that it doesn't want to be in a zircon, and eventually the zircon just overrides it, incorporates it, and that's what these little excursions are. But again, what's that going to do? It's going to make your temperature seem hotter than it really was. So all these things. And lastly, this is fascinating because how does this Hadean distribution compare to, well, you've seen how it compares to mafic zircons, to zircons from the moon and so on. But when you compare it to granites from, the Phanerozoic, the last, say, 500 million years, this is, in fact, the characteristic distribution of zircons from terrestrial granitoids. And it plots in a distribution and with a temperature that's consistent, not with water-saturated melting, not with minimum melting, not with, in fact, having an infinite source of water, but where the melting was driven by actually the dehydration of the hydrous phase. This is the absolute norm. This is, in fact, you look in the Himalaya, all the granites in the Himalaya look like this, with one exception. And that's this guy here, which actually looks more like the Hadean distribution than anything else we've seen. And what's fascinating is, in fact, this is the one Himalayan leucogranite that is known from trace element data to, in fact, have originated by water-saturated melting. So here we have a terrestrial case where you can independently document that this granitoid, which is freakish because, as I say, of the many dozens that have been documented in the Himalaya, this is the only one that looks like the Hadean, and it's the only one whose trace element complement really requires it to have formed by water-saturated melting. Okay. Now, there's another way we know that there was water around when these things formed, is because every time a zircon grows, it takes a little gulp out of the surrounding melt. So you get inclusions. For example, here's an inclusion of muscovite, and we've analyzed for titanium, and we've dated the thing at 4.023 billion years, you can see. These inclusion assemblages broadly come in two flavors. One that I'd characterize as sort of Himalayan type, quartz muscovite case bar rutile. This is when you go to a Himalayan leucogranite, to one of these collisional environments. This is the sort of assemblage you see. Okay, quartz feldspar muscovite. And another one that I characterize as Cordilleran or Andean type, hornblende biotite plagilmonite. This is if you were to go to the Andes today and grab a chunk of volcanic rock that just popped out. This is the sort of assemblage you'd see. So we've got a couple of opportunities here. Here's a zircon. You can see the nice cathodoluminescence imaging. These are these tree rings. Here's where we dated this guy. And here's a hornblende biotite assemblage. Here's muscovite quartz. In most cases, in fact, or in many cases, the muscovite, this is a classic mica, has this extraordinarily high aspect ratio, gives us confidence that, this thing, in fact, was incorporated into the into the crystallizing zircon rather than represents a secondary feature. Well, these inclusion assemblages give us a couple of ways to look at the pressure at which these zircons form. Okay, the titanium's giving us temperature. We can use hornblende barometry to estimate pressures, how much aluminum is in the hornblende, or we can use the muscovite, this white mica, because as you increase pressure on white mica, it in fact, a pure mica wants to have a silicon performing unit of 3, but as you increase pressure, you can incorporate more and more silicon at the expense of aluminum by, in fact, a reaction that somebody showed yesterday. And what we find is there's a couple of different groups. Here's age of the zircon. You see what we're calling broadly group 1, with silica per formula unit of about 3.1 to 3.25. And then another group up here. And the two efforts we've made, we've seen both groups represented. This is more complicated than it needs to be, but here's pressure increasing. Here's temperature increasing. This is a so-called pseudo-section from this internally consistent thermodynamic database called Thermocalc, which in fact is trying to tell you what the phase relations would be in a rock of a particular chemistry. So what we've done is we've taken classic continental granite, and where you see these warm colors, Thermocalc is telling us muscovite plus liquid is stable. Hirschman's looking a little skeptical about this, and in fact, I thought I would go to my grave without ever having done a pseudo-section, but that's not important. Although I will point out that, in fact, here are our data from Group 1, and it's actually a pretty good correlation between where Thermocalc is predicting muscovite plus liquid and the existence of muscovite-bearing inclusion. One of the things that's really astonishing to us is when we looked at 1,700 Hadean zircons for the inclusion assemblage, the most common assemblage, remember this is early Earth, this is 4.3, 4.35, 4.38 billion years, the most common mineral association is quartz plus muscovite. And for those of you that did undergraduate metrology, you'll know that that's surprising. That's so continental. Okay, for those of you that were math majors, that's so continental. So, in addition to having this characteristic of having come from a melt chemistry, we call it perluminous, that is indicative of melting a shale. Okay, this is how the planet. Why is the ocean salty? The ocean's salty because granite somehow forms out of mantle rocks. Okay, it gets near the Earth's surface, and the feldspars don't much like it. Your beach is made out of quartz because the quartz is happy up here, but the feldspar wants to rot into clay, and when it does that, it enriches aluminum and silicon. But the potassium and the sodium and the calcium get swept out to sea, and that's why the ocean is salty. That's why there's a lot of calcium out there. That's why a lot of sodium, and so on. So it looks for the world. You don't get muscovite, or at least 99.9% of the granitoids on this planet that we can document that have primary muscovite have it because they're a remelted peelite. They're a remelted clay. Okay. So it's hardly smoking gun diagnostic, but it's certainly suggesting that the source of these zircons had been through a sedimentary cycle. Okay, when we actually translate the four different barometers into pressure, we get a range of values from basically 6 kilobars to 18 kilobars. That's a pretty big range. The temperatures are all, as you saw, between about 650 and maybe 720 or 30 degrees or something like that. So surely these granitoids are forming in some kind of thermal boundary layer. These are not granites that are forming in the convective part of the mantle, say. And so if that's true, then we can use Fourier's law to relate the apparent thermal gradient into and assume some conductivity. I don't care what conductivity you pick. It's going to be an apparent or local heat flow. And when you look at this, the data arrayed in this fashion, what's remarkable is here's the present day average global value from the Earth. Okay, so our values are ranging by sort of 1/2 or 1/3 of the present value. But shouldn't it have been hotter at 4.3 billion years ago? Yeah, Dave.
Can you be sure that all these mineral inclusions were actually in chemical equilibrium?
No, that's going to be tough, and some aren't. Some, for example, some of the inclusions we've looked at, the rock itself, when I go hunting for Hadean zircons, I look for green stripes in the quartzite, because zircon is a heavy mineral. I mentioned we have to use special chemicals to separate it out. So it actually finds a home with other heavy minerals like chromite. And chromite, chromium oxide, isn't real happy in sediment, metamorphosing in the crust, and it wants to react with the clay portion of the rock to make a green mineral called fuchsite. So actually, we go for the fuchsite layers because that's telling us where the heavy minerals are. Some of these inclusions, some of the muscovites clearly have been talking to the host rock because the fuchsite has 1.5% chromium in it. Most of these micas have detection limit, 0.0 something or other, but basically detection limit chromium. Those ones haven't been talking to the host rock, but a couple have, and let's ignore those. And I say, pretty clearly, the muscovites that have the shape of a book or something, you could hardly imagine the implausibility of reconstituting or having a fluid that had exactly the composition of a seladonitic muscovite constituting itself in the appropriate crystal form inside a zircon that had formed in the past. So in most cases, we have textural evidence that these zircons are primary. And the fact that they vary, the fact that there's such variability in the silica suggests that certainly since they formed in this quartzite, they haven't reequilibrated, or they'd all have the same silica per formula value. Yeah?
So when we would date this sulfur or micas with some other
Yeah, that's an excellent point. So why don't we date these inclusions? I don't know if you saw, they're really tiny, okay? And so we couldn't pluck these out and date them by conventional isotopic means. They're just too small, okay? But, pardon me? A nanosims isn't going to help you. A nanosym, if you had a tenth of a micron beam, and remember, these muscovites are, sort of order, nanogram size. Rubidium in a muscovite might be 1,000 ppm, right? So you've got a nanogram. Now you have to multiply by, 10 to the minus 3 or 4. And you're going to have to do a chemical separation to get strontium 87 over. So in fact, it's just not feasible. Well, you could, but again, you're looking at a sample size that's maybe 2 orders of magnitude smaller than the minimum you'd need to basically overcome the blank in your lab. Yep.
Those numbers for those group 2 micas, 13 to 16 kilobars and 16 to 18 kilobars.
Yep.
Can you go back and go to the thermocalc?
Well, they're not on there.
Right.
Yeah. See, here's the problem. The thermocalc, up at around 10, 11 kilobars, thermocalc says, I don't have a solution model to explain how you could get that much iron into muscovite. So basically, we can use thermocalc for group 1. For group 2, we use an empirical calibration of, that's been generated by studies where you have an independent barometer and seladonite in white mica barometer, and it produces this calibration that translates those very high silica per formula unit into pressures of between 16 and 18 kilobars.
I guess we can read a lot into these data, and perhaps it's dangerous to read too much into them. But when I think about making pearl-luminous granite in anything like a normal petrologic environment, I'm thinking of a fairly shallow crustal environment, right? 5 kilobars, something like that. And you have these. That's certainly what I would see for most pearl-luminous granites that are here. So I can have 2 interpretations. One is that this was an exceptional petrologic environment for making the granites, or these are meta pearl-luminous granites, right? That they were magmatic rocks that later had a metamorphic history.
You're asking a lot. Okay, what Mark's... Well, what you'd need, in fact, is to then, if you grow a zircon and you capture this mica that that had this particular silicon aluminum ratio because it was in contact with this high pressure assemblage, and now you take that zircon, you put it into a different environment, it's going to be real hard for you to, the zircon host isn't going to help at all. So you're going to have to freely communicate with the outside world in order to up that.
So your interpretation is that you're going to basically granite formation at the base of what we would consider to be quite thick rock.
No, actually, I think this is melting right off the slab. You're at a very different thermal regime, and
You said really magic word. The slab.
okay, well, I'm getting ahead of myself. Here's the. Let's drive this home. Where do you see? Okay, so we're looking at a variety of folks have speculated what the global heat flow in the Hadean would be, and 200, 250, even 400 milliwatts per square meter. So pick any one of these values, and it's going to be a third or a quarter of what you might speculate Hadean global heat flow to be. Well, where on this planet do you make magmas? Would you make a magmatic zircon in a heat flow environment that's 1/3 or 1/4 of the global average? There's only one place. There's places on the planet that are cool, but lots of places with low geotherm, but only one place with low geotherm that you make magmas, and of course that's in a subduction zone. Okay, where so here's my sort of cartoon characterization of today. Sort of scaled, you're melting maybe under Mount St. Helens at 75 or 80 or 85 kilometers, something like that. The scaling would be very different in the early Earth with a higher, let's speculate the higher heat flows as proposed by Norm Sleep and others. So this is there's no question, I think, that we're seeing evidence of, so this is now coming back to your question, why do we infer melting in a low geothermal environment? Because we have independently temperature and pressure information from these old zircons. So they're forming in an environment of essentially water saturation. There is a sort of an infinite amount of water available, and under temperature conditions that are remarkable relative to what we speculate. Dave?
Yeah, just wanted to make a comment while the audience is sitting here stunned with the visitor's introduction and the Hadean kicking in. That is the geotherms from that, and if it's a correct interpretation, represent the local heat flow, and to then extrapolate that as a global heat flow, you would need to have that environment like globally covering it. So there's still probably places of exceptionally high heat flow, these heat pipes and other heat transfer mechanisms that would still allow for really high heat flows.
Just like on the modern planet. Just because the geotherm 80 kilometer. No. I'm not arguing that the global average is. Well, I'm certainly not suggesting that any speculation about Hadean heat flow is meaningful. Okay, just simply that's the background.
So there is, of course, a body in the solar system that has extremely high global heat flow, and we know this. It's about 2,000 milliwatts per square meter, and I'm talking about Io. We also know that Io, in most places, must have low heat flow. How do we know that? We know that because it's got mountains, high mountains. So it must have low heat flow in most places. Now, I can't use Io to solve your problem directly because it doesn't have water, and so I can't take the argument further. I'm just making the point. You can have both things. You can have very high heat flow and have low heat flow in most places. Io doesn't.
Yeah. Well, so I'm proposing here nothing more than you see on the planet today. That in above subduction zones, you have low local apparent heat flow, whereas if you go to the mid-ocean ridge, in fact, that's compensated for by much higher than average heat flow. So I'm not suggesting there was low heat flow. Simply that
The comment is just that the global heat flow is dominated by the places where the highest heat flow comes out, not the lowest.
Sure, no, as it exists today, and almost certainly would have existed then.
Can't leave that slide yet.
Oh.
Are you implying that you have to have this?
What I'm
Just comparing with
you're putting words in my mouth. I haven't said that.
You said the slab. I heard you say it.
That doesn't imply subduction. I mean, this is a slab. Yeah. What I'm suggesting is there has to be some kind of underthrust environment in order to and actually, if you'll let me leave this slide, I can sort of go to my more interpretive.
I'm sorry. First of all, what Dave Stevenson just suggested, in iotectonics, you get low heat flow and crust formation by this unbelievably rapid burial of accretion.
And do you have molten sulfur under those mountains where there's low heat flow?
Well,
No.
The point being is that it's possible that your burial mechanism is not.
No. Okay. Good. No. Let me say that. Yeah.
Hi, Mark. So these barometers that you're showing show sort of the lower heat flows along all the data that you showed, but there's also the distance of the two groups within the barometry measurements. Do you think the distance of those two groups is significant with respect to information?
I'll tell you what. Let's skip ahead a few slides because all will be. And this is the oxygen. Here's sort of what actually bulk Earth or zircons coming out of the mantle would look like, or in fact zircons on the moon. And the Hadean distribution is shifted to heavier values. And that simply has been interpreted that the way that you make minerals with heavy oxygen, enriched in oxygen 18, is by having clays. Clays love at low temperatures to grab the heavy oxygen. So let's really, I'm going to have to skip this here. This is pretty cool. We'll come back to this in the, oops, I won't skip this. This is a recent documentation by Rick Carlson and his co-workers, a remarkable site up here in eastern Hudson's Bay. Help me here, Rick. Nuwagatuck, yeah. And what's interesting is that this is not, a zircon that you picked out of a crushed quartzite. This is, a suite of rocks, of mafic rocks, in fact, underscored the fact that they appear to have been derived by hydrous, low-degree melting of a relatively primitive mantle source. The stunning thing is that the mafic rocks yield a 142, right? Of course, a 147. This is a proxy because the 146 is all gone, right? 4 billion years ago. So a neodymium isochron with the, remember this is the neodymium isotope that's produced with a half-life of 68, 70 million years early in Earth history. The correlation corresponds to an age of essentially 4.4 billion years. So instead of rooting around in this dirty quartzite, here appears to be a suite of rocks that is preserving this ancient age with a reasonably low uncertainty. Now, it's complicated because if you look at the adjacent felsic rocks or the part of the suite, you get ages that range sort of from whole rock ages of 3.7 billion years. There's clearly a disturbance in these secondary isochrons of 2.9 or 3. The accessory minerals yield ages. The oldest one would be Rec 2.7 or something like this, and so it's complicated. But it's hard to get around the fact of that correlation that we just saw. You could interpret it as an isotopic fractionation that occurred at 4.4 billion years in the adjacent mantle, and has been preserved, or maybe magma mixing of early separated sources produced this array. But when you do this, and I guess we're not going to have time to expose that here, but the arguments are so incredibly convoluted as to, in fact, make the simpler explanation that these are 4.4 billion year old rocks seem plausible. Yeah.
Yeah. I have a question now that one of these Concordia lost comes up. So what if you have, so you obviously lost some uranium, or if you lost it in two stages, you get a unique age?
You mean could you derive anything because of the extra control you have from the two isotope system? But all you can do is extrapolate back to Concordia, and this says, the oldest that we're going to extract from this is about 2.8 billion. But in fact, it could have started up here and been reset.
Yeah, could you, if you do something at, let's say, 3,000.
Oh, sure. Now, if you say, the lead loss event was here, that is a very different story. That's going to intersect Concordia maybe up at 4.4 billion years. But what you'd like to see is an array of data that's, parallel with that line rather than pointing towards present day. It could have had 9 events, yeah. But, that's the limit of what you can get out of this information. It doesn't mean that the source rock weren't older. It just means that we've lost that. If it was, we've lost that information. Okay, well, here's a summary. So if you want to explain everything that I've shown you, including the Nuavituk data, you're going to need to explain why there was, at least in some zircons, this oxygen 18 enrichment. This, I think, is a really profound constraint. This single bullet-like Gaussian from the titanium, that the inclusions are hydrous, and I say S&I type, perluminous and metaluminous, sort of Himalayan and Cordilleran or Andean type assemblages. This predominance that's at 2/3 or more, 70% of all the inclusions in these zircons are quartz or muscovite, and essentially co-equal abundance. That at least some of the zircons have hafnium isotope compositions that are within spitting distance of the solar system initial. Crystallization under apparent geotherms, not too different from modern Earth in convergent margin environments. We didn't talk fractionation, plutonium, uranium. We'll talk about this in the tutorial next week. At 4.35, Bruce Watson and Dustin Trail have taken these zircons and devised a way to estimate the oxygen fugacity from which they formed. You heard a lot about that earlier in the week. And the oxygen fugacity looks a lot like FMQ, which was close to nickel-nickel oxide, which is, if you remember, looks like the present oxidized upper mantle. So at 4.35, the source of these zircons looks like the modern oxidized upper mantle. These are definitely continental zircons. We have evidence from 142 and other systems that there was very likely a global silicate differentiation, potentially creating crust, and then the preservation of these 4.4 billion year mafic crust. So let me just quickly say things that might pop into your head. Well, how about impact zircons? It's not a very appealing mechanism at face value because you essentially are going to produce a melt sheet mostly by decompression of the target rocks, and in which case it's going to be difficult or impossible to get water to the site. If you were to take the present ocean and put it into the atmosphere, about 300 bars, and have it, in fact, talk to a melt sheet exposed right at the surface, the solidus of that system would still be above 800 degrees, nowhere near the 680 that we need. When we actually go, this is Matt Weilicki's work. Some of you saw his poster the other day. Here's the Hadean zircons. This is what mafic zircons look like. This is what Icelandic rhyolites, zircons out of those Felsic rocks that form in Iceland. Matt's looked at zircons from the preserved impacts we have, Vredefort, Sudbury, Moracoang, Papagai, Manicouagan. And what he finds is, in fact, that impact zircons look like Icelandic zircons and mafic zircons. They don't look like the Hadean zircons. Actually, in fact, derived a model in which we used a late heavy bombardment type flux to hit a compositionally diverse planet, because we've only got 4 or 5 impacts that make up less than 1/10 of 1% of the surface area of the Earth. Maybe we just got unlucky. Maybe we hit the wrong targets to make zircons down here. This is the result of our global model. In fact, it's similar in shape and slightly offset to higher temperatures than what Matt found. But again, it's clear that impacts are not. Just reiterating here, Morbs, the chemistry doesn't fit. Mafic complexes, crystallizing granophyres don't work. The temperature distribution and the chemistry is different. Kimberlites, as you saw, don't work. But, what about other ways to get low geotherms? What about, various sort of sagduction scenarios where you've got some primitive vertical tectonics, and then a cold region here, downwelling, and you take weathered material that's been through a mature sedimentary cycle and sagduct that into the mantle. Well, the pore space for carrying water is going to be very limited. So you're going to make melts greater than 800 degrees. And in true fact, as these things sink, you're going to be going through a series of dehydration reactions. First, temperatures of compaction, and then temperatures of 200 and 300, green schist type dehydration. By the time you get up to partial melting, there'll be insufficient water, and certainly not enough water to, in fact, act as an infinite reservoir. And here's Jeff Davies, sort of, you can't have plate tectonics in the Hadean, but maybe you could build up a pile of basalt 90 kilometers thick and melt at the bottom. You can do that, and you will produce a felsic melt, but that melt will form at 920 degrees, and if it makes a zircon, the zircon will, in fact, reflect. If the zircon was saturated in that phase, it would reflect these extremely high temperatures. You just couldn't make a 680-degree peak. Okay, I think we're... So this is probably where I wanted to be when you...
But for your sagducting metasediments, why did they retain less water than subducting metasediments?
With the thermal structure that I showed you on that in that convergent margin scenario, the temperatures, I guess I could race ahead just about at the end here. But
it's something that you're assuming about the temperature pressure path of sagduction.
Yeah. Sagduction, you've cut yourself off from the ocean. Under thrusting with a background geotherm that's 2 or 3 times higher than present day means that where you're potentially forming water, instead of getting to water saturated granite minimum melting temperatures at 70 kilometers depth, as in present, back then you might have been doing that at 18 and 20. So simple dehydration rate, dewatering of sediments in a Hadean scenario could in fact provide flow of molecular water into to either melt directly off the slab or ascend into the overlying. One thing that we're gearing up to do is actually look at the phase petrology in a Hadean type geotherm. So we know it pretty well for a modern subduction environment. Okay, but now imagine that you've increased the geotherm by, say, a factor of going from 12 degrees per kilometer to 40 or 30 or 40. There's an immense amount of water coming off between 10 and 20 kilometers depth. You're dewatering sediments where the hanging wall is at minimum melting temperatures. You don't do that today, and we might not have in fact done that for 4 billion years. So why do present granites in the Himalaya look different from the Hadean? Because we've removed the source of making granites so far from the surface as to, in fact, exclude a pipeline from the ocean directly into the magmatic zone. So it's the special thermal conditions of the Hadean that would permit this, that we've long since lost a geothermal structure that would permit that modern day. I'm going to skip ahead. I'm using Jun Korenaga's scaling just as an experiment. Let's imagine that he's right. You heard a little bit about this in Jeroen's talk. Here's a calculation using the thermal structure of oceanic lithosphere that, in fact, after 120 million years, his oceanic crust at 2 centimeters a year becomes neutrally buoyant, and it's now been thrust underneath some model Hadean crust. Here's his predicted thermal structure, and this is a very simple model. But what I'm showing you in black is the range of temperatures that we see in the zircons, basically 650 to 750 degrees, and in the white triangle, the range of pressures that we see in the various barometers. It's an overly simplified model. Simply, now imagine that, in fact, you're instead of having to bring water down to 80 kilometers, you in fact can dewater the slab at 20. Pardon me? This is C. Yep. Okay, let's end there. So what's the simplest explanation for everything that we see? I showed you that list of a dozen observations that we've derived out of these various systems. It seems to me that the data is more consistent with the Earth actually looking, more like it does today than we previously thought. That there's some kind of continental-like crust, at least with a continental-like lutetium hafnium reservoir, around very early on in order to, in fact, preserve. I can hold a zircon in my hand that effectively has a solar system initial hafnium isotope composition. So even though that zircon is only 4.32 billion years old, the stuff it's made out of hasn't been remixed back into the global silicate system since 4.5 billion years. So I need a raft not to hold that zircon, but to hold the stuff from which that zircon was made. Various lines suggesting that we're getting these two characteristic inclusion assemblages because we see, in fact, both Andean and Himalayan type convergent margin interactions. This signal that we see, especially in the hafnium, this essentially data that are giving something close to the initial isotope composition of the solar system, right down to about 4 billion years. I didn't point this out, but after 4 billion years, you never see that signal again. That data is heading towards a modern value of hafnium, epsilon hafnium of minus 120. Okay, Rick, top of your head, what's the most non-radiogenic hafnium that's documented in the post-Hadean record? Minus.
Post-Hadean?
Yeah.
In the modern world, or make a big question?
Yeah, but I'm thinking, But nobody has said, hey, here's a rock that has a present-day epsilon hafnium of minus 120. No, not even a factor of 2, I think. Yeah, right. Okay, so there must have been active this signal that we're seeing in these old zircons of this really unradiogenic continental-like signal. We don't see a trace of it since. It could be hiding somewhere, or in fact, it just could have been remixed back up into the mantle, and you take, Morb source, and you take this continental material, and you mix it at a fine enough scale, it'll look like primitive mantle. Okay, and to say, but by about 3.6 billion years, she's all gone. The last thing I want to say is it just happens that today a group is leaving the Boston area, Ben Weiss and some coworkers, to head to the Jack Hills to do something. And I was inspired to mention this because of Bruce Buffett talking about the origin of the magnetosphere. and how interesting it would be in terms of understanding core dynamics and heat flow to have some measure. The first thing I have to point out is that these Hadean zircons, each of them actually has remnant magnetism. Here's an image from a squid mass magnetometer that Ben runs at MIT, showing you these 100-micron zircons have, and as we investigated, it looks as though, for the most part, it's because of tens of nanometer scale pyrrhotite inclusions. That's a sulfide mineral that fortunately has a really high Curie temperature, 680 degrees or something like this. So in principle, I mean, let me pose a hypothetical. What if every 4.4 billion-year-old zircon doesn't have remnant magnetism, and every 4.3 doesn't, but every 4.2 and 4.1 and 4 does? You know, would that mean that there's a signal that the geodynamo started at 4.25 plus or minus 0.05? That would be, you know, really cool. The downside is that I know that these zircons haven't experienced temperature conditions since they were deposited in their host quartzite 3 billion years ago that would have disturbed a pyrrhotite Curie temperature. But I don't know what their thermal history is prior to that. Well, in fact, with Bruce Watson, we've developed a method to actually determine which of these zircons have or haven't experienced temperatures higher than 550 degrees since they formed. So Ben and the group is heading to the Jack Hills. We can't use, we've gone to a lot of trouble to separate 170,000 zircons and mount them and analyze them. We can't use any of them because they were all separated using not just the heavy liquids, but a Franz isodynamic separator, which in fact has disturbed the, didn't think of this 10 years ago. So we have to start from scratch. But also, we don't want to use them because Ben has in fact detected from our existing samples evidence of reset magnetism from lightning strikes. So they're taking a drilling apparatus out there. We're going to drill down more than a meter. In fact, get really through the regolith here, and try and get fresh material for which there'd be no ambiguity from this. So, you know, real high risk attempt, but potentially high payoff. And we actually thank the National Science Foundation for providing funds for this jaunt. Anyway, so that's the story. Thanks. Yeah, the monazite you do. In fact, you find monazite inclusions. But the monazite inclusions, in fact, have been open systems. The monazite is a phosphate mineral, and uranium can have 300 or 1,000 or 5,000 ppm uranium. Monazite is sort of typically 5% thorium and 1% uranium. So the monazites have become metamict and essentially, you know, fractured the zircon, and then during a later sort of upper green schist grade metamorphism, we believe because they've all updated to an age of 2.6, which is this regional, yeah. So the monazites, no help.
Why is the magnetism created by pyrrhotite?
You know, no, you're transcending my ignorance here. This is what Ben tells me. Magnetite would have, you know, pyrrhotite good, magnetite bad. So we're happy. Or maybe what he's saying is that it'll only be the pyrrhotite-bearing ones that we'll look at.
Okay, Mark is here disconnecting his computer. If you have more questions, but probably everybody else wants some food.